In a previous video, we noticed that the simple equations that we use to obtain the Darlin controller, which tries to obtain the first order response that I've sketched here in green at the sampling intervals, has the unfortunate result that in some cases the continuous response of the system actually oscillates back and forth. We saw that we could see this effect when we observed the output of the controller. So if we have a look at the output of the controller that would be associated with this input, the output would be changing rapidly between positive and negative values, and this is how we could see that ringing is taking place. Now, the two other controllers that we're going to do the design of in this subject are designed to accommodate or to alleviate the problem that the Darlin controller has. So the first version of this controller design is to use a second order target, and so unlike the Darlin controller, which uses a first order target function, the Vogel-Edgar controller uses a second order target function, and this allows us to much more cleanly approximate the output. So we'll still obtain exactly the prototype function at the outputs, but with the Vogel-Edgar controller, with an ideal model, we will obtain exactly the target function, and in most cases what that will correspond with on the controller output side is a much nicer controller output. So typically we will do a couple of moves straight near the start and then have less movement going forward. There may be some correction, so there may be moves starting in one direction with a corrected move instead of actually something like that, something over there, going back and moving further along. So this is the basic idea behind accommodating these ringing effects using the Vogel-Edgar controller. Now, so both the Darlin controller and the Vogel-Edgar controller are prototypical controllers. In other words, we have a desired output function and we are solving for the controller that will lead to that desired output function. In all of these cases, we sometimes have to do some iterative design in order to find a controller that actually works well. It is also possible to use discrete controllers, or to use a discrete version of the IMC controller. And so you'll recall that the IMC controller structure is different from these controller structures. So these controllers all had just a simple target GC that we were targeting with a process model, and fundamentally we were trying to calculate GC given a known output prototype. For the IMC controller, we have a slightly different setup. We distinguish between the traditional straightforward feedback controller GC and the IMC controller GC star, where we now have a model in parallel to that system, and where we are subtracting the model prediction from the measurement and using that as the feedback target. So this is the IMC structure, and in IMC we are going to see the same kind of structure that we saw in the other discrete controllers. We will also be able to target some specific desirable behavior, but the way in which we will do that will be to know that if this is y and this is y is p, that y over y is p is going to be equal to the uninvertible portion of the control system model multiplied by a filter. Now, if we're doing this in discrete, we have a discrete filter, and what this allows us to see is that the undesirable parts, and over here are unstable poles that would become non-causal if we inverted them, as well as ringing poles, and then we can choose the filter so that this combination looks the way that we want it to look. So we can find some combination of the filter and the undesirable parts of the plant that will give us the behavior that we want. And so this allows us very clearly to see where we should accommodate the undesirable parts of the plant, and it allows us clearly to make decisions where in the other prototypical approaches we kind of had to guess. We guess a prototype, design a controller, see whether that controller led to ringing, and then we had to maybe stick a plaster on it by neglecting the ringing poles in the case of the Darlin. In the case of Vogel, we know that for a wide variety of parameter values, we end up with a relatively reasonable controller. However, the downside of the Vogel controller is obviously that we have a slightly more complicated prototype. In the case of IMC, we will be designing GC star, and we will be simulating G tilde. In all of these cases, in the cases where we are using this for discrete control, we will obviously have sampled and held the controller outputs. So we'll be working with a held version of the model, and in fact we will also be working with a sampled version of the measurement output. And so for the case of the discrete IMC, everything within this box is actually going to be discrete. We'll have a discrete controller, we'll have a discrete model, we'll have the analog version of the system over there, and we'll have a hold element to connect the controller to the system, and we'll have a sampler to connect the real system with all of the rest of this discrete system.